going on? We were doing big O. We were doing like big O analysis on different sortings. That's where we left off here. Structures and algorithms in Python. So we'll continue on with this. I think I can hear my mother-in-law just rolled up. So we were learning essentially that how the different sorts work and what their big O was. Either their log n, base n, or 2n, or n to the second, or no, n to the second, or 2 to the n, which are really slow. The exponent ones are really slow. But in some cases, some of the sorts on a smaller scale are better, when there's like 10 inputs or less or something like that. So
Quicksort big O. On average, quicksort has a big O of O(n) to log n. In the worst case, and assuming we don't take any steps to protect ourselves, it can degrade to O(n square. Partition has a single for loop that ranges from the lowest index to the highest index in the array. By itself, the partition function is O(n). The overall complexity of quicksort is dependent on how many times partition is called. Worst case, the input is already sorted. An already sorted array results in the pivot being the largest or smallest element in the partition each time, meaning partition is called a total of n times. Best case, the pivot is the middle element of each sublist, which results in log n calls to partition.
So I wish there's a way to determine the pivot where you could take, but how would you know what the highest and lowest values are? Right, without sorting it. Okay, that answers my own question. Because it pivots, if your pivot's in the middle, it'll do, essentially from the pivot outwards, it'll sort it. But if your pivot's at the end, it'll have to go through all the numbers to say that it's either greater than or less than whatever the pivot is. What causes quicksort to break down to n squared? An already sorted list, because then the pivot selection is bad. What is quicksort's worst case big O complexity n squared? But they also said that there's different implementations of quicksort.
Fixing quicksort. While the version of quicksort that we implemented is almost always able to perform at speeds of O(n log n), its big O is still technically O(n)s too, due to the worst case scenario. We can fix this by altering the algorithm slightly. Two of the approaches are: shuffle input randomly before sorting. This can trivially be done in O(n) time. Actively find the median of a sample of data from the partition. This can be done in O(1) time. Random approach. The random approach is easier to code, which is nice if you're the one writing the code. The function simply shuffles the list into random order before sorting it, which is an O(n) operation. The likelihood of shuffling a large list into sorted order is so low that it's not worth considering. Median approach. Another popular solution is to use the median of 3 approach. 3 elements, for example, the first, middle, and last elements of each partition are chosen, and the median is found between them. That item is then used as the pivot. This approach has less overhead and also doesn't require randomness to be injected into the function, meaning it can remain deterministic and pure.
What does shuffling quicksort's input do? Makes it really slow? No. Makes the algorithm unsafe for production use? No. Practically ensures a runtime of O(n log n), slows down the algorithm? No. Practically. practically ensures a runtime of on log n. Why is the median of 3 approach sometimes used? It doesn't require randomness and impurity.
Why use quicksort? Pros: very fast. At least it is in the average case in place. Saves on memory. Doesn't need to do a lot of
These things are fast.
copying and allocating. Cons: typically unstable. Changes the relative order of elements with equal keys. Recursive: can incur a performance penalty in some implementations. Pivot sensitivity: if the pivot is poorly chosen, it can lead to poor performance. All this said, quicksort is widely used in the real world because the trade-offs are often worth it. For example, it's a default in PostgreSQL, a popular open-source database. I'd also like to shout out timsort, a hybrid of merge sort and insertion sort that was Python's default from version 2.3 to 3.10. As of Python 3.11, it's been replaced by PowerSort, which makes small but meaningful improvements.
If you need a stable sorting algorithm, which would you use? Quicksort, none of these. No sorting algorithm is stable. Merge sort? Probably merge sort. Which would you be more likely to use in a large production system? Bubble sort. Because they're the same once it gets large data sets, right? And so if quicksort is unstable. Wait, what? Why? Fast in the average case. It's an in-place algorithm, memory efficient, and it's more memory efficient. It has some drawback, like potential being unstable instead of pivot selection. All right, so bubble sort's like the slowest. It's generally considered one of the simplest but least efficient sorting algorithms. It has a ON squared, the complexity in both average and worst case, making it the slow for large data sets. Yeah, but I thought quicksort was slow on large data sets too. But it's more efficient on smaller ones.
Selection sort. Another sorting algorithm we never covered in depth is called selection sort. It's similar to bubble sort in that it works by repeatedly swapping items in a list. However, it's slightly more efficient than bubble sort because it only makes one swap per iteration. Selection sort pseudocode. For each index, set smallest IDX to the current index. For each index from smallest IDX plus 1 to the end of the list, if the number at the inner index is smaller than the number at smallest IDX, set smallest IDX to the inner index. Swap the number at the current index with the number at smallest IDX. Assignment. Complete the selection sort function. It should sort the input list nums in ascending order using the selection sort algorithm. The function should then return the sorted list.
Alright, so let's say n is equal to the length of nums. And then set smallest to current index. So for I in range n, smallest IDX equals I. For each index from the smallest IDX plus 1 to the end of the list. for j in range of I to n I plus 1. If the number at the index is smaller than the number at the smallest index, is that what it's short for? Set smallest index to inner index. So if num's at the j index is less than nums at the smallest IDX. Set smallest IDX to inner index, so smallest IDX equals the j index. Swap the number at the current index with the number at the smallest index. The same, I just use an extra variable.
Polynomial versus exponential. Broadly speaking, algorithms can be classified into two categories: polynomial time, exponential time. Polynomial versus exponential. Technically, ON is factorial time, but let's lump them together for simplicity. An algorithm runs in polynomial time if its runtime does not grow faster than n squared k, where k is any constant, in 3, etc., and n is the size of the input.
Oh, using
To
k
put it
for
simply,
constant.
polynomial time algorithms can be useful, but exponential time algorithms are almost always too slow to be practical, unless you're trying to force someone to be slow, like in the case of cryptography and security. Even when n is as low as 20, 2n is already over a million. n2, 2 then. 2.
Polynomial algorithms are blank than exponential algorithms faster.
Polynomial time equals p. Back in the 1970s, some computer scientists wanted to come up with a good, descriptive name for the set of polynomial time algorithms. After much deliberation, they settled on the letter P. Naming things is hard. The hand-wavy takeaway is that problems that fall into class P are practical to solve on computers. Problems that don't fall into P are hard, slow, and impractical.
Algorithms in P are blank than algorithms not in P. More practical to solve.
reduction to p. Let's take an exponential time algorithm and fix it up so it can run in polynomial time. The Fibonacci sequence is a sequence of numbers where each number is the sum of the two numbers before it. Like this, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. We want a function that, given an index in the sequence, returns the Fibonacci number at that index. For example, fib 0 minus 0, fib 1 minus 1, fib 2 minus fib 3 minus 2, fib 4, 3 fib 5 minus 5 fib 6 minus fib 7 minus 13. Here are the implementation details to do it in polynomial time. The input n represents the index of the desired Fibonacci number. Initialize three variables: grandparent equals 0, parent equals 1, and a placeholder current to store the new Fibonacci number at each step. Write a loop that iterates n-1 times. For example, if n equals 2, no iterations occur. Inside the loop, 1. Set current equals parent plus grandparent. 2. Adjust the ancestor values, parent and grandparent, to maintain the sequence. Once the loop completes, return current. Assignment. Our data scientists at Locked In have found that the growth of the average influencer's follow count is roughly the same growth rate as the Fibonacci sequence. In other words, after 6 weeks of good social media posts, the average influencer will have 8 followers. After 7 weeks, 13 followers, and so on. The trouble is, our current implementation of the fib function takes so long, exponential time, to complete, that when our influencers navigate to their analytics page, it often never completes loading. Adjust the fib function using the given algorithm to achieve polynomial runtime.
All right. Initialize these variables. Grandparent. Parent. Current. Placeholder current to store a new Fibonacci number at each step. So current will be 0 too. Write a loop that iterates n-1 times. For example, if n equals 2, no iterations occur. So the loop is n-1 for I in range. Inside the loop set current. Parent plus grandparent. Adjust the ancestor values, parent and grandparent, to maintain the sequence. So grandparent equals parent. Parent equals current. Current. You don't have to initialize. You don't have to initialize current equals 0. If n is less than 1, we immediately return n without using... Oh, that's right. This kind of covers it here. Okay, so this is kind of like redundant. It's covered here.
Order tooth n minus exponential. Ov-tooth n is the first big O class that we've dealt with that falls into the scary exponential category of algorithms. Algorithms that grow at an exponential rate become impossible to compute after so few iterations that they are almost worthless in practicality. Assignment. At Locked-In, we need to be able to compute the power set of a set of influencers. It has something to do with targeting segments of an audience with ads. I don't know. I just work here. A power set consists of all possible combinations of elements in a given collection. For example, the power set of 1, 2, 3 is 1, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 3. We'll work with Python lists instead of sets for simplicity. An empty set will just be an empty list. Complete the power set function using the following algorithm. Check if the input list is empty. If it is, return a list containing an empty list. The power set of an empty collection contains just the empty set. Otherwise, create a list that contains an empty list. This will hold the final collection of subsets. For each element in the input list, 1. Create a new list to hold the new subsets that include the current element. 2. Iterate over each existing subset. 1. Create a new subset by adding the current element to the existing subset. 2. Append this new subset to the list of new subsets. 3. Extend the main collection of subsets with your newly created subsets. Return the final collection of subsets. Observe. Notice how the power set output gets exponentially larger with each iteration because its complexity class is O2n. If we could calculate one subset per millisecond, completing the power set of just 25 items would take approximately 9 hours, and that's not accounting for the massive amounts of memory we would need. 40 items would take over 34 years.
Check if the input list is empty. If it is, return a list containing an empty list. The power set of an empty collection contains just the empty set. If not, input set. Create a list that contains an empty list. Right. So the final collection of subsets. Alright, so subsets is also a list of empty lists. For each element in the input list, create a new list to hold a new subset, include current element. Yeah. Iterate over each existing subset. For each element in the input list, element in input set, Create a new list to hold the new subsets that include the current element. So new subsets. The list. Iterate over each existing subset. So for subset in subsets, create a new subset by adding the current element to the existing subset. So subset plus element. Is equal to append this new subset to the list of new subsets. So new subsets list append new subset singular. Extend the main collection of subsets with your newly created subsets. Alright, so subsets.extend. Subsets. And the final collection of subsets. If length equals 0, or if not input set. If not, alright.
Big O categories review. Big O, name, description, and A pool. Cat review. O1, constant, best. The algorithm always takes the same amount of time, regardless of how much data there is. Example, looking up an item in a list by index. O log erindic. Logarithmic, logarind. Great algorithms that remove a percentage of the total steps with each iteration. Very fast, even with large amounts of data. Example, binary search, OON, linear, good, 100 items, 100 units of work. 200 items, 200 units of work. This is usually the case for a single non-nested loop. Example, unsorted array search, ON log n, linear arithmetic. Okay, this is slightly worse than linear, but not too bad. Example, merge sort and other fast sorting algorithms. ON2, quadratic, slower. The amount of work is the square of the input size. 10 inputs, 100 units of work. 100 inputs, 10,000 units of work. Example, a nested for loop to find all the ordered pairs in a list. ON3, cubic, slower. If you have 100 items, this does 103 equals 1,000 units of work. Example, a triple nested for loop to find all the ordered triples in a list. O2 to n, exponential horrible. We want to avoid this kind of algorithm at all costs. Adding 1 to the input doubles the amount of steps. Example, brute force guessing results of a sequence of n coin flips. ON, factorial, even more horrible. The algorithm becomes so slow so fast that it's practically unusable. Example, generating all the permutations of a list.
Which algorithm is the fastest? Constant? N or log n? There's no log n. N is just the fastest here. Considering the following code, Names is an array of strings. Define get names and index names I. Return names I. What is the big O complexity of this function? Just it's n. Right? One input, one output. Oh, or is it one? Or is it not n? Treats the element as a given index in O1 time. O1 means constant time, operating same amount of time, no matter how large it is. Okay. Oh, names I does not depend on the size of the list. Gotcha. Calculates the number of times given number can be divided by 2 before it becoming equal to 1. This is n, because it's one loop. There's a log n. I think it's n. Fuck, it's log n. Because once it gets down to 0, until x is less than 1. If we start with n, we need to find k and there's that n to 2k, which means log divided by 2 divided by k was less than 1, which means k is approximately log 2n. Okay. Consider the following functions for 2 questions. Half sections returns a list of lists. For example, n12 results in 0 to 12, 0 to 6, 0 to 3, 0 to 1. Okay. Well, I is greater than 0. Col is an empty list. For j in range of I plus 1, col dot append j rows. I divided by 2, return rows. I don't think it's not n squared. There's only 2 loops. I don't think it's n, n, n. 2n or log n, log n. I think it's log n, log n. God damn it. Give us 2n. Fuck. It's 2n. It's just 2 loops. What's the most reduced form of the function's complexity? O(n). This is 2n, you just get rid of the component or whatever. Constant.
Exponential growth sequences. At Locked In, we are interested in simulating the exponential growth of an influencer's followers over a certain period with an adjustable growth factor. Assignment. Complete the exponential growth function. Given the initial followers count n, growth factor, and number of days, return a list containing the exponential growth of followers for each day. For example, initial followers 10, growth factor 2 days, 4 growth sequence 10, 20, 40, 80, 160.
Initial followers is N, growth factor. This factor and number of days is days. So we need to make a list, an empty list. But it's not empty because we have an initial followers account. So we put N in there. And then we'll append this value in our function to give us total followers or growth. So for I in range, days, growth factor is factor. So multiply the factor into N. And then append growth with this value. Factor times growth sequence. Growth sequence minus 1. Hold on a second. Is this okay for an answer? There are other ways to write it, like using a previous value in a list. Okay.
Travel time limit. Locked In is planning a campaign where influencers are given a time limit to visit as many countries as possible. However, the travel time between countries follows an exponential growth pattern. This means that the more countries influencers visit, the longer it takes to travel to the next one. It's a small growth factor, too, but it's still exponential. It's a bit strange. We figure it's because they take more and more time lollygagging in each country for pleasure. Assignment. Write a function num countries in days that takes a maximum number of days, max days, and a time increase factor factor, then returns the number of countries an influencer can visit within that time limit. Influencers start by spending 1 day in the first country. For the next visit and every visit after, the time in the current country is multiplied by the factor to determine the time required for the next country. Incomplete visits are not allowed, and the cumulative time traveling cannot exceed the max days. For example, max days 2. Time factor 1 point, countries visited 1, max days 3, time factor 1.2, countries visited 2.
Oh. All right. So while time left is greater than or equal to time in country, subtract time in country from time left. Count is what? Countries visited. So add 1 to the count for the country visited. And then multiply the time in country by the factor, the inputted factor. I think that's it. And return the count, because that'll give us how many countries.
Introduction to data structures. Starting with this chapter, we're going to focus on how we can store and organize data in a way that allows for even better algorithms. Data structures are just organizational tools that allow for more advanced algorithms. Some examples: stacks, last in, first out; queues, first in, first out; linked lists, a chain of nodes, efficient for inserts and deletes; binary trees, a tree where each node has up to 2 children; red-black trees, a self-balancing binary tree using colors; hash maps, a data structure that maps keys to values; tries, a tree used for storing and searching words efficiently; graphs, a collection of nodes connected by edges; assignment, implement the count marketers function. It should accept a list of strings, job titles, and return the number of users who've set their title to marketer. Locked-in users sometimes use different casing in their titles, so make sure to account for that. Count equals count marketers, programmer, marketer, doctor. Print count, prints 2. Tip: the .lower method can be used to convert a string to lowercase.
Count marketers function, accept a list of strings, job titles, and return the number of users. Alright, so we're counting, starting at 0. Then we have to loop through it. So for titles, job titles, dot lower. If title dot lower equals marketer, then we add 1 to the count. Oh, 1 marketer. 2 marketers. All right. For titless and job titless.
What are data structures? A data structure is a data organization, management, and storage format that enables efficient access and modification. More precisely, a data structure is a collection of data values, the relationships among them, and the functions or operations that can be applied to the data. Wikipedia definition. In other words, a data structure stores data, organizes data so that it can easily be accessed and modified, contains algorithmic functions to expose the ability to read and modify the data. You're already familiar with some of Python's built-in simple data structures. List, an ordered collection of items. Animals equals cat, dog, mouse. Dictionary, collections of key value pairs. Car equals brand, Ford. Model, Mustang, year 1964.
Yeah. Alright. Data structures store data and allow access to it efficiently. Don't use algorithms, false. Are web-scaled databases, false. Are only used by CS professors to scare business majors into dropping the class, false. Store data and allow access to it efficiently. Which is not a data structure. Tuple, MySQL, dictionary, array. What is MySQL? The software. Relation database management system. Array. Isn't it MySQL? It's the program, right? It's a database management system, DBMS. Okay. Arrays are data structures that are stored elements in contiguous block memory, typically of the same type. While Python leans on lists for many of the same purposes, in other languages like C or Java, arrays are found in data structures. Okie doke.
Lists. Okay, we know what lists are, but from a data structures and algorithms perspective, what are they good for? Let's break it down by operation. Append. Appending an element to the end of a list, e.g. cars.append forward, is, on average, O1. We go directly to the end and add the element. Index. Accessing an element by index, e.g. cars2 is O1. We go directly to the index and return the element. Delete. Removing an element from the middle of a list, e.g. cars.pop2 is ON. We have to shift all the elements after the deleted element down one index. Search. Searching for an element in a list, e.g. cars.index forward, is ON. We have to iterate over the list until we find the element. In other words, lists start to struggle in two primary areas: when you need to frequently delete elements from the middle of the list, when you need to frequently search for specific elements in the entire list. Assignment. We need to display a user's last job title on their profile. Implement the last work experience function. It takes a list of our players' work history, strings, and returns the last place they worked. Assume the list is ordered from oldest to most recent. If the list is empty, return none.
Takes a list of our players' work history strings and returns the last place they worked. Assume the list is ordered from oldest to most recent. So we would have to start at like -1 to get to the 0 spot, to the first spot in the list. Oh, okay. So we need work experiences in the -1. It's empty, return none. So if not, Otherwise, return it. Oldest is first, right? So -1. Yeah. Length of work experience less than 1. I just did my if not first. I like putting the not case first. I can ask the bear. What do I ask? Is it more socially accepted? It's fucking AI I'm asking. To put the non-case first, or the other way around? Typically, it's more accepted and common to test for edge cases such as none or empty list at the beginning of the function. Okay. The approach avoids deep nesting and quickly exits the function when a specific condition arises. Which style do you think helps the reader understand the function logic faster? I like putting the nots first, because then it's like, it's restricting the data down into what you can. Because if you don't have work experience, right, it just ignores that shit, essentially. Whereas this, it's like, it measures, I mean, it's doing the same thing. It measures the length of the work experience, and if it's greater than 0, then it will return the first spot of the work experience.
Lists quiz. Answer the questions based on this code from the last assignment. Def last work experience experiences. If len work experience is 0, return work experiences -1, return none. Looking up an item in a list by index is much faster than searching for items using iteration. O1 vis ON.
What is the big O complexity of last work experience function where n is the length of the work experiences array? Log n, isn't it? Or is it n log n? Well, I need to get this. It's log n. Fuck. Fuck. Oh my god, it's 1? Really? Alright, I don't know why this is 1. Length of work experience. Getting the length of a list is a 0-1 operation in Python. Okay. Work experiences, length of work experience -1. Assessing an element by index is also. Oh. I thought that was n, or log n. Assessing an element by index is 1. Oh, okay. The function isn't looping through the list or doing any operations. Okay. I got you. There's no loops. Gotcha. Why is index lookup so much faster than iteration? The index is stored in the back of a physical book, and as we know, turning pages is blazingly fast. The computer can jump straight to the location of the index. An index is like an address of an item in a list. Index lookup just requires scanning the array up to the given location. Full iteration goes all the way to the end of the list. It's this one. God damn it! Just gonna jump straight to the index. Oh, I'm thinking about loops again. Suggests that the index still requires scanning through elements. This is incorrect. Index lookup doesn't need to scan. It just jumps directly to the correct location. Gotcha. I have loops on the brain. Fruit Loops on the brain.
Stacks. A stack is a data structure that stores ordered items. It's like a list, but its design is more restrictive. It only allows items to be added or removed from the top of the stack. It's called a stack because it behaves just like a stack of physical items. Imagine a stack of plates. It's easy to take an item off the top of the stack, but you can't really get to the items in the middle or at the bottom without removing the items on top first. You'll often hear a stack referred to as a LIFO, last in, first out data structure. Whoever decided to take this simple concept and slap a nasty acronym on it should be forced to program in Prolog for the rest of their days.
So you know fucking acronyms? It's the government. The government has a fucking hard-on about doing like acronyms. They have acronyms with acronyms in them. That's how fucking stupid it is.
Assignment. In this chapter, we'll build a stack from scratch. A stack will be useful at locked in when we need undo-redo functionality. For example, a user can add other users to their connections list and then undo the last connection they added. Stacks are a great way to implement undo functionality.
Also, just as a side note, LIFO and FIFO, those are business things. First in, first out, last in, first out. It's for like stocks and tax harvesting.
For now, we'll just focus on two methods, push and size. Notice that the stack class already has a constructor and the underlying list that we'll use to store items. Complete the push method. It should add an item to the top of the stack. The top of the stack is the end of the list in our implementation. Complete the size method. It should return the number of items in the stack.
Complete the push method should add an item to the top of the stack. The top of the stack is the end of the list. Okay, so we're just appending. To self.item. Complete the size method. It should return the number of items in the stack. So just the length of self.items. Oh, items. Yep.
Stack speed. You might be wondering, why would I use a stack instead of a list? Isn't this just a list with fewer features? And you'd be right. A stack is a list with fewer features, but that's the point. By restricting the ways we can interact with the data, we guarantee that certain operations are blazingly fast. Here are all the operations a typical stack supports, along with their big O time complexity. Operation big O description. Push O1. O1. Add an item to the top of the stack. Pop 1. Remove and return the top item from the stack. Peek 1. Return the top item from the stack without modifying the stack size. O1. Return the number of items in the stack. All O1. That means no matter how many items are in the stack, these operations will always take the same amount of time. Stacks are really fast and are usually the best choice when the behavior of a stack is all you need.
The way that I conceptualize it, the plate idea is actually pretty good, but I kind of conceptualize it as like a filing cabinet with files and papers inside of it that you can perform functions on, essentially. So like pushes, add an item to the top of the stack. So add an item, put a folder in the front, popper, remove and return top item from the stack. So pull out the front folder, peek, look at the front folder, size, return the number of items in the stack, count the number of folders in the thing. It's kind of like how I'm thinking of it, at least.
A stack is a revered data structure in computer science, known for its simplicity and efficiency. This last in, first out structure is like a stack of plates in a cafeteria. You add one to the top,
Right.
and you take from the top, ensuring a seamless flow of data manipulation. If you've ever used Control-Z to undo an action, you've interacted with a stack. A stack can do 3 interesting things. Push, which adds an item to the top of the stack, pop, which removes the top item, and peek, which reveals the top item on the stack without removing it. Stacks are simple and stacks are fast. That's why programming languages use them to manage memory and why your bad code results in a stack overflow. They're also used to build back buttons, evaluate mathematical statements, and build algorithms that find the shortest path between 2 points. Pushing, popping, and peeking are all order 1 operations, which means if you can use a stack, your code will be blazingly fast. It's pretty easy to build a stack on top of the built-in list type in Python. After all, if you turn a stack on its side, it kind of looks just like a list, right?
Yep.
Well, the built-in append method can be used to push onto a stack, and a list's built-in pop can, well, pop. And we can index directly into a list to be able to peek. So is a stack just a crappier list? Well, kind of, but stacks are great because they force us to keep our code simple and efficient. If we use a stack, we'll never accidentally iterate over a list of 10 million items and freeze up the user's machine. If you enjoyed this explanation, subscribe to the channel. I'll see you in the next one.
All right, which operation is big O1, size, push, pop, peek, all of them? Where can items be added and removed from a stack? The top? Pop and peek. All right, I gotta take a leak. I'll be right back. Yeah, I'll be right back. I guess. I might not come back. Fuck y'all. Eat the eggs. All right. Pop and peek. We poppin'. So we're writing pop and peek. Complete the peek method. It should return the top item from the stack without modifying the stack. If the stack's empty, return none. Complete the pop method. Should remove the return the top item from the stack. Stack's empty, return none. The length of self.item equals 0. Return none. The top item from the stack without modifying it, so just self.items. One. And then pop is same as this. Can I do just stop pop? Am I not supposed to do that? You can use or remove an item from the list by an index. The last item in a Python list can be accessed by -1. How did they use delete? Item equals self items -1. Delete self items -1. Return item. Oh yeah, I'm supposed to do that and not use pop. I don't think inside of the function pop. Alright, stack review.
Stack review. All supported operations are O1 by themselves. However, some tasks, like getting to an item at the bottom of the stack, have a higher time complexity because they require multiple pop operations. Stack operations are limited. No searching, no sorting, no random access. Stacks, like all abstract data types, can store items of any type. What makes it a stack is the behavior of the operations, not the type of data it stores. Stacks are often used in the real world for function call management, undo-redo functionality, expression evaluation, browser history.
What could be stored in a stack? Your mom's phone number. Yeah. Objects, integers, any of these. Your mom's phone number. Hey, why is the last call from your mom? From my mom to you? If you want to get an item at the bottom of a stack, what is the big O to retrieve that item? O1 because of pop operation, right? You just pop everything. No? Stacks can be searched using binary search. Oh, is it? Oh, it's ON because all items need to be popped first. That's right. So like if you need to pop one item, whatever time it takes for that, perform that times X amount of times you need to pop. So it'd be N.
Using a stack. Locked-in supports a basic scripting language. It allows technically savvy HR managers to write scripts that can automate repetitive tasks on the platform. The language makes use of parentheses to group operations together, and we need to be able to check if the parentheses in a script are balanced. Balanced parentheses. Parentheses are balanced when each parentheses has a corresponding parentheses, and the pairs of parentheses are properly nested. For example, unbalanced parentheses. Assignment. Complete the isBalanced function. It takes a string as input and returns true if the parentheses in the string are balanced and false otherwise. Use an instance of the provided stack class in stack.py to keep track of the parentheses. You only need to consider the characters "and" for this challenge.
Character put string if character equals open parentheses. Pop peak size push. stack function, say, let's say stack equals stack function. Because then I want to push it, right? Okay, push the open one and size the outside one. I think it's dot push character stack push. Size. False case, and then otherwise top. I like the way they wrote their close parentheses better.
Debounce stack. On the locked-in platform, we use a stack to store the last few actions a user has taken. This allows us to implement an undo feature. When a user clicks the undo button, we pop the last action off the stack and reverse it. However, sometimes users accidentally take an action multiple times in a row. For example, a user might accidentally click the Add Connection button twice. In this case, we don't want to add the same action to the stack twice. We only want to add the action to the stack if it's different from the last action. Assignment. Complete the debounce stack class. It should inherit from the stack class. Override the .push method in the debounce stack class. If the action on the top of the stack is of the same as the action being pushed, then the push operation fails and nothing happens. Otherwise, use the .push method of the stack class to push the action onto the stack.
Override the push method in the debounce stack class. So define push. If the action on the top of the stack is of the same as the action being pushed, then the push operation fails. Otherwise, use the push method of the stack class to push the operation onto the stack. Self-item. action on the top of the stack is the same as being pushed, and the push operation fails, nothing happens. I'd otherwise use the push method of the stack class to push the action to the stack. If a self dot size equal to 0. Or self dot peak does not equal item, then stack push self and item. What's super? Python super allows a subclass to access methods and properties from its parent's class. Oh, that's right. Like super init. Ah, I forgot about this. I could have done this.
What is a queue? A queue stores ordered items. Again, kind of like a list, but again, like a stack, its design is more restrictive. A queue only allows items to be added to the tail of the queue and removed from the head of the queue. It's called a queue because it behaves like a queue of people waiting in line to order coffee. In the Lord's tongue, American English, we say, "I'm waiting in line," but in the UK they say, "I'm waiting in a queue." Alan Turing was British, so we just gotta let them have this one. The first person to get in line is also the first person to be served. Get out of line. So, you'll often hear a queue referred to as a FIFO, first in, first out, data structure.
Queues are one of the data structures that you already understand, even if you don't know it yet. Ever stood in a line for 2 hours just to be told that Mickey had to leave and couldn't meet your daughter? Great, you were an item in a queue. Now, you might already know about stacks, which are last in, first out. Well, queues are the same thing, but first in, first out. Queues are useful in code because they model real-world systems. Amazon packages on a conveyor belt that my wife ordered for herself when I forgot her anniversary? That's a queue. Humans waiting for the new iPhone that has the exact same features as their last one? That's a queue. The 69 bugs.
Excuse me, sir. Am I on a 12 or a 13? I'm on a 13 Pro Max. But the phone I had before that was a 7 Plus, okay?
On your dev team's ordered backlog, queue again. Queues are everywhere. Whenever items are processed in the order they're received, that's a queue. Queues do 3 things. Enqueue, or push, which adds an item to the back of the queue. Dequeue, or pop, which removes an item. item from the front of the queue, and peek, which reveals the item at the front of the queue without removing it. It sounds like just a normal Python list, right? Well, kind of, but by building a queue class, we limit ourselves to the enqueue, dequeue, and peek operations. There's no searching allowed, and that's why it's fast. Want to create a new queue? Just create an empty list. Want to enqueue an item? Use the insert method to add it to the beginning. Want to dequeue an item? Pop it from the end of the list. Want to peek? Index directly to the last item in the list. Assuming that your implementation of the enqueue, dequeue, and peek operations are all as efficient as they can be, you will get an order 1 time complexity on each operation. The code using your queue will be really fast, no matter how many items are stored in it. If you do choose a basic list to build your queue, the enqueue speeds will be order n, which is quite a bit slower, but you can always use a linked list to speed that up. If you enjoyed this video, please subscribe to the channel, it really helps me out, and
Alright. What's a real example of a world queue? The set of possibilities in a dice game? No. Absurdly long line of millennials without children waiting to get into Disneyland. Lane's collection of totally cool and totally not lame Lord of the Rings action figures. A stack of plates in a cafeteria. Millennials waiting to get into Disneyland.
Queue class. Assignment. Logged In uses a queue to keep track of the order that recruiters should use to reach out to job seekers. Implement the following operations on the queue class. Queue.pushItem adds an item to the tail of the queue, index 0 of list. Queue.pop removes and returns an item from the head of the queue, last index of list. Queue.peek returns an item from the head of the queue. Queue.size returns the number of items in the queue. Note: you'll often hear words used interchangeably in programming. For example, here we're saying push and pop, but enqueue and dequeue are also common words for the same ideas. Term 1, Term 2, description. Push, on queue, adds an item to the tail of the queue. Pop, dequeue, removes and returns an item from the head of the queue. Tips: the underlying data type we're using is just a list. Don't forget to guard against index errors. The .insert list method may be helpful.
Alright, so we're gonna insert the item. Insert an item at a given position. The first argument is the index of the element before which to insert. So A insert 0x inserts the front of the list with A insert length of A, x is equivalent to A dot appendix x, append x. So we need to insert index 0 of list, so 0 and then item. First is index, second is item. Removes and returns an item from the head of the queue, last index of the list. Can I just pop it? I should pop it though. Just dot pop. from a previous question that we did. Turns an item from the head of the queue. Zero. Turn the number of items in the queue.
Queue speed. So how fast are queue operations? Well, in an optimized queue, they'd be operation big O description. Push O1, add an item to the back of the queue. Pop O1, remove and return the front item from the queue. Peek O1, return the front item from the queue without modifying the queue. Size O1, return the number of items in the queue. Just like a stack, all operations are O1. No matter how many items are in the queue, these operations will always take the same amount of time. The reason to choose a queue over a stack is all about ordering. Queues should be used when you need to process items in the order they were added. LIFO, stack, versus FIFO, queue. A problem. Our current queue class has a problem. Take a look at the push method. Def push self item, self.items.insert item. It's not O1. The list's insert method has to shift all the other items in the list down to make room for the new item. We'll solve this very solvable problem soon.
What is big O complexity of push, pop, peek, and size operations of an optimized queue? O1. Tom Cruise fast. Wait, how fast does Tom Cruise run? How fast? He's tiny. Oh, he only runs 15 miles an hour. Tom Cruise has been estimated to run an average speed of around 15.3 miles an hour. How fast Tom Cruise does Tom Cruise run from his gay thoughts? Hey, catch me, gay thoughts. Oh, I think I already have this in my notes. If an item could be anywhere in a queue, what is the big O complexity to retrieve that item? 1. N, because you have to pop. Say you have to pop 10 times, it's going to take 10 times the speed of a pop. Yeah, I'm done. Why is our list-based queue push operation ON? Because you have to search for the perfect spot to insert the new element. Nope. Because you have to remove everything from the queue before you can add a new element. Nope. Because you have to move all the elements over by one index to make room for the new element. Yep.
Matchmaking queue. In Locked In, users that are founding companies can join a matchmaking queue to find potential co-founders for their projects. We'll use the queue class we've built to manage the matchmaking process. Notice the search and remove method on the queue class in queue.py. It breaks the rules of a traditional queue data structure, but will be useful in solving this real-world problem. It's okay to violate academic constraints as software engineers, as long as we understand the trade-offs involved. Assignment. Complete the matchmake function that simulates users joining and leaving the matchmaking queue. The function should take a queue instance and a user tuple containing a name and action, either join or leave. Use equals Bob, join. Use equals Alice, leave. For each call to matchmake, if the action is leave, search the queue for the user and remove them if they are in the queue. If the action is join, push the user's name onto the queue. Lastly, check if the queue has at least 4 users in it. If so, pop the first 2 users from the queue and return the following string. User 1 matched user 2, where user 1 is the first user popped and user 2 is the second user popped. If there were less than 4 users in the queue, return the following string. No match found.
Complete the matchmake function simulates joining and leaving matchmaking queue. The function should take a queue instance and the user tuple containing the name and the action, either join or leave. For each call to matchmake, if the action is leave... Okay, so we have to split the tuple. So if we say name... an action is equal to the user, that will split the tuple. If action equals leave, then search the queue for the user and remove them. Search the queue for the user and remove them if they are in queue. So if name in queue not items, right? Queue items remove our other action is going to be join, push the user's name onto the queue. Lastly, check if the queue has at least 4 users in it. So if queue size is greater than or equal to 4. If so, pop the first 2 users from the queue and return the following string. User 1, user 2. pop, 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 pop. If there's less than 4 players in the queue, return the following string. No match found. Yeah, they did it like this. They took name as user first position, actions user in second position, but you just do name then action for the tuple. Search and remove. Oh, there's a search and remove. Search and destroy. Do 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 do. A little bit different. I didn't realize there was a search and remove function.
Linked lists. Remember how the push method on our queue is on instead of o1? Def push self item. Everything in self.items has to shift, up a position, which takes on time. Self.items.insert 0 item. Let's fix that. To build a faster queue, we'll use a linked list instead of a regular list array under the hood. A linked list is where elements are not stored next to each other in memory. Instead, each item references the next in a chain. Nodes. Our nodes will be represented by a simple class with 2 fields. Val, the raw string value that the node holds, e.g. Carla, James, etc. Next, a reference to the next node in the list assignment. Let's lock in and make locked in faster. Complete the node's constructor. Set its val field to the provided value and its next field to none. Complete the node's setNext method. It should set the next field to the provided node.
Our nodes will be represented by a simple class with 2 fields. Value, the raw string value that the node holds, example Carla, James, etc. And next, a reference to the next node in the list. Complete the node's constructor. Set its val field to provide a value and its next field to none. Oh, spit my tongue. Motherfucker. complete the node set next method, it should set the next field to the provided node. Oh, how's it going?
Linked list versus list. A linked list is a collection of ordered items, so it's similar to a normal list, also called an array or slice in other languages. Items in a normal list are stored next to each other in memory, and to get an item from a normal list, we have to use a numbered index.
Fucking gif of fat fingers just like hammering a dial pad, like bunch of numbers at the same time.
Car equals cars 420. You can think of the index as simply an offset from the start. The cars list in this example refers to the start of the list, and 420 is just the 420th item in that section of memory. With a normal list, all the data is stored in the same place in memory, and the index is just a way to find the right spot. In a linked list, there are no indexes. Each node contains two things: the data itself and a reference to the next node in the list. Iterating over a linked list requires starting at the head node and following the next references until you reach the end. Current car node equals head car node. While current car node is not none, print current car node.val. Current car node equals current car node.next. Frankly, linked lists can be annoying to use and incur more overhead, so why use a linked list at all? It's because sometimes linked lists are much faster to make updates to, particularly when inserting or deleting items from the middle. In a normal list, if you insert an item in the middle, you have to shift all the items after it down one spot, which takes on time. In a linked list, once you've traversed to a given node,
Okay, so they're putting 100 in, so you have to move everything.
insertion is 01, because you can simply update two references.
Because it does not care about its position in the list. It cares about its reference. Gotcha. I'm gonna take a leak and get some lunch. I'll be back. All right. We can find an item in a linked list by sending up thoughts and prayers, popping an item off the list, iterating through all the nodes by following the next references, indexing directly to the item with an index number. Wait, what? Oh, the next references. Oops. Linked lists have a faster time complexity than regular lists when it comes to insertions, right?
Iterating. Even though iterating with linked lists kinda sucks compared to the simplicity of arrays, normal lists, we've got to do it. Although the implementation is more complex and slow, we can still make it easy for users of our class by providing an thgotour method. The yield keyword. The yield keyword in Python returns a value, kind of like return. However, it's used to turn the function into a generator function. A generator function creates a new function object. When that function is called, it executes the code in the generator function until it hits a yield statement. At that point, the function pauses and returns the value of the yield statement. The next time the function is called, it picks up right where it left off. Def create message generator, yield hi, yield there, yield friend, gen equals create message generator, first next gen, print first, prints a second equals next gen, print second. Prints there, third equals next gen, print third, prints friend. Every time you call create message generator, it creates a new generator instance. To continue from where you left off, you need to assign this generator to a variable, like gen in the example above. This way, when you use next or loop over the generator, you're continuing with the same instance rather than starting a new one. Assignment. The linked list class is a wrapper class that uses the node class we already wrote. Complete the init method. It should set the head field to none. No other node points to the linked list's head, first node, so the linked list class itself needs to keep track of it. We'll use the term head and tail like this: head node, node, nash node, nash node, nash tail node.
Nash.
The direction of flow above might feel opposite to what you're used to with a queue, but it's really the same. Above, I'm using arrows to show which nodes are pointing to which other nodes. In a future lesson, when we implement a queue using a linked list, we'll add elements to the tail and remove elements from the head. Complete the iter method. It should be a generator function that yields each node in the linked list from the head to the tail. By overriding the utter method, Python will allow us to use a for loop to iterate over the linked list. L equals linked list, L add first, L add second, L add third. For val in LL, print val. Create a reference to the head node, e.g., node equals self.head. Use a while loop to iterate over the linked list until node is none. Yield the current node. Set node to the next node.
Should be head field set to none. Okay. Complete the iter method. Should be a generator function that yields each node in the linked list from head to tail. By overriding the iter method, Python will allow us to use a for loop to iterate over its linked list. So yields each node, so the node is equal to the self.head, right? So while node is not none. Yield. Node value. Yield the current node's value, so dot value. And then set node to the next node. Alright, string object has no attribute value. I don't know what the issue is. Futia! Thanks, baby. Got pocket soda? Yeah, pocket soda. Where should we watch?
And I've compiled some of my... Okay, so it's been a few days since Dawn of the Hunt 0.2 dropped, and I've compiled some of my thoughts. I've just been writing down things that have been bothering me as I play. Overall, I think the endgame itself is in a bit of a better state in some ways and worse in others. So starting off, I don't actually mind the lower damage across the board. I thought the game needed a power nerf for sure. However, I don't really know why they nerfed early game damage so much. I was asking people in my chat, I was looking at other streamers. It looked like almost nobody was having a good time. I thought the damage was pretty reasonable for leveling before, except for like Perfect Strike on Warrior, obviously that like one-shot at bosses. So yeah, I feel like they definitely took away too much damage there. and it's more of like an annoyance thing. So it's not even, I don't really even care that you're so weak, but there was another major problem that was kind of revealed to me that I didn't fully realize the extent of until this patch. Oh, Merry Christmas, by the way. So, I started as a melee character mostly. I mean, it was hybrid, it was Huntress, right? So, the low damage really revealed to me that the boss fights in this game are actually not good. I do not like most of them. The only boss fight I actually had fun on this patch was Viper in Act 3. And like Gunnar is cool aesthetically. Count Gunnar, the end of Act 1. He's cool aesthetically, but I don't know. All of these bosses, I mean the entire game has this one major problem for me, especially on melee. You don't really notice on a range because, well, you're ranged. So when you're near a boss, your character feels like they are lathered up in some kind of butter or like lube or something. I don't know. You like slide around everywhere, you're desynced, you're rubber banding. It's really bad. So obviously on ranged you kind of miss that problem, but it feels really bad. It's not crisp. You're bouncing all over the place. You're just constantly getting like pushed around, and the game does not handle it well. And then there are some fights like the Ultimatum Ascendancy with the bird, or not the bird, I think it's the Chimera, Uxmal, and he just like constantly flies around. I'll put a clip there showing my fight in like 3 times speed or something. And he is just constantly off the ground. And when you go to fight him in melee range, he's constantly in a giant AoE of degen shit. It's just terrible. Some fights are like that. There's a lot of fights where they just stand in their degens, and melee is rough to play in this game. The game feels like it kind of wants to be Dark Souls, but it's failing at it, in my opinion. If you play ranged, it can kind of masquerade as it. I think when you play melee, it really falls apart. And it kind of maybe hits a niche of people who want things that seem like they're very mechanically intensive, but in reality, I think they're just annoying to fight rather than difficult. So that's my main problem with combat in this game. It's not just bosses too. It happens on enemies. You just like get bounced around them, and I don't know. It's especially with the bigger enemies. I don't know if it's a problem with their hitboxes being too big or something, but really bad. And this is not a new problem either. It's just hasn't been fixed. And then I don't know why zone layouts change on League Start. So if you didn't know, in this game, like, map layouts will change based on the season and move everything around, rotate it, and I'm pretty sure, I mean, they mentioned they're gonna do it. I'm pretty sure they did it. I could be misremembering what softcore trade was at the start last time, but pretty sure it changed around. And one thing I do know is that playing different game modes, like if you go from softcore trade to hardcore SF, the layouts will be different. I don't know why they do this. I don't know why they like this idea. They mentioned it as a way to like make it more fresh and more fun for players. Make the campaign not so boring once you've done it 100 times. I do not think it accomplished that whatsoever. I don't know how that would be more fun. Basically, it is 100 times harder to learn where to go in this game than it is in PoE 1. Granted, these zones are supposed to point towards which way you run in the zone, but it doesn't work in every zone. And I feel like really it only works in Act 1 to a degree. And once you hit Act 2 and 3, it doesn't work at all. So maybe once they fix that, it'll feel better and it won't be such a big issue. But
Act
running
2
around
is just
aimlessly in such
fucking
huge zones is
Jackson
not
Pollock
good.
painting of
Granted,
directions
they
to go.
did just put out this changes to Act 3 areas, so maybe that'll clear up Act 3 a little bit. We'll see. So, everything in the game has a huge delay. Like everything. Opening a portal, having to go click the well instead of just portaling back into your map. Waiting for bosses to die. Waiting for monsters to die. Waiting for lore to play out in town. It's bad. Bad for long-term players. It's fine for the story gamers who are going to play once and never play again. But I'm tired of waiting 30 seconds for Count Gunnar to drop his loot. And now even the new endgame stuff, the corruption zones, not this, but before you cleanse it, whenever you kill the boss, you have to wait for Doriani to come up, and he comes and gives the boss like a hand job for 5 minutes, and then they explode, and then you get the loot. It's stupid.
I mean, 5 minutes for a hand job.
I hate
is
how many
actually not
delays there
that
are like
long.
that in this game. You have to wait for so much stuff. And then loot is still missing. They've addressed this and it'll be added, but still a lot of stash affinities. And if you don't know what affinity is, it's like you click the item and it'll go into the correct tab automatically. A lot of them are still missing, like runes and some socketable stuff. So that really disrupts the flow of like looting quickly, depositing it. That'll be fixed. That one's not a huge deal.
Just throw it into quad tab. And then never look at it.
I do not like cheat death omens. Okay, this one's not a cheat death omen that I have, but there are omens that essentially you'll hit low life and it will fully heal you. I do not like the addition of this. I do not like anything like that. I think it's stupid. And then, additionally, or related, and perhaps the biggest issue, defense options in this game are, or no, second biggest issue, I'd say the actually fighting bosses and stuff being pretty bad is number one. But number two, for the worst thing, defense options in this game are really, 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 really abysmal. Pretty much every build will go pure energy shield or hybrid energy shield evasion. I don't know why I don't know why they took life at the off the tree at this point. It doesn't make sense to me. And then you can, I mean, the only way you can go life essentially is like if you're going blacksmith with getting a bunch of life and then you get a bunch on your ascendancy. I don't know. Stacking strength like gemling, I mean, you could do it on smith too, so you can actually get a decent amount of life. I don't know. It's weird. You have essentially 3 defensive options in this game that actually are like not terrible, and 2 of them are essentially the same. Overall, not a fan of not much defense on the tree. I'd like to see them address that at some point. That's probably my biggest concern. I mean, as a predominantly hardcore player, even though I play softcore in this game because I don't think it's good enough yet for hardcore. So I don't think I would ever league start this game on hardcore in its current state, because overall it's just not good enough all around in pretty much any way. Oddly enough, something that wasn't included in this game that might make defense feel better, and it's really weird that this wasn't included in me, is guard skills from PoE1. If you don't know what that is, they're essentially like reactive defensive measures. And the only thing I can really think of in this game is like the Jade thing on Warbringer. I don't know, I feel like that plays perfectly in this game. It's a reactive like button you press to get defense, and it's interactive. It's, I don't know.
Ray shield.
I don't know why there's so, like, you only have offensive options in this game when you're building your character. You don't really ever think about what kind of defense you're gonna go, because you already know what one you're gonna go. You're gonna go energy shield. And then, last thing, why are trade site prices still manually updated? It often baits noobs because the prices are like sorted incorrectly. I don't know why. I heard a cow. It's probably that. I don't know. Okay. Yeah, I don't know why it's like there's like one employee that goes into the trade site and he updates the prices himself, but he only does it like once every month. So for the longest times, it's just sorted incorrectly. And people are like, why is this item on your build 5 divines? And I'm like, it's not, it's 20x. But divines like start at like 5x. So it lists the divine listings first, even though that's not the real price. So that's pretty frustrating.
She's talking about like the pricing on the trade website doesn't adjust to the exalt to divine to chaos orb ratios. It changes over the course of a season. So like right now, a divine orb is like 50 exalt, but by the end of the season, it's almost like 500 exalts per divine orb.
Those are the only things I could think of, like, as I played that were really, really bothering me. There's probably a few more.
So what will happen is if you stick in 50 exalted orbs equal to 1 divine on the trade websites, those are equal values. So if something is like later on exalts become nothing, they're 500 to 1, then like 100 exalt item looks like a 2 divine item on the trade website when it's really 1/5 of a divine. It was kind of fucked.
Overall, the lower damage in endgame is good.
It's up Inferno.
The new uniques they added are pretty good. I do like the endgame stuff they added.
I got a sick helmet. I got a helmet that was like % increased dex, int, and strength. And it actually was really good. Still leveling with it.
They seem kind of lost or what. I don't know what's going on. But
I also got a belt that when you're on low life or low mana, when you use your flask, it instantly restores your 100% of your shit. Or it instantly applies the flask, which is cool.
It's kind of weird. I don't know. I'm hoping once the game is like fully, like content-wise with the campaign and everything, and all the classes are added, they can really start to hammer this stuff down. My like copium is that they're spending all their resources trying to build all that stuff from the ground up, which would take more time than fixing it later. So that's my hope. Other than that, those are my main pain points, so that's about it. If I think of more, I might make a second video.
Top down game. Oh yeah, it's just a genre though. Like, actually, one of my most favorite games ever is a third-person shooter. The SOCOM 2 U.S. Navy SEALs. Look at this. He's playing terrorists. Terrorists against SEALs. The terrorist guns suck, though. Like, the SEALs guns were so good.
Oh, he's right in front of you. There you go.
First-person shooter? Yeah, like Minecraft.
You know what it is? I need to fucking switch my gun.
Sometimes first-person shit, though, just, like, makes me feel really weird.
The 77
Dude, M14 was sick.
just has too much
But both sides get M16. The AKs suck.
spray.
STG doesn't do that much. M16's sick, but it only does 3 3 burst. But if you could master the 3 burst on the M16, it was
I
really
need
good.
something more precise. What's better, the 47 or 74?
47.
What should I use, boys?
I used to snipe. I used to snipe in that game. This game.
Saharan Algeria and the Kamchatka Peninsula in Russia. There are also 5 difficulties that will
PS2 graphics, man. We could play this game. Yes, K Simulator. %, historically accurate too. He's using the car to body block him. Oh shit. Tofu delivered, 3 out of 6. I actually want to watch that Minecraft movie. I had a bootleg version. Come on. I don't know what the audio quality is like on this though. Sometimes the bootlegs are not great.
Got him. He's fine. He's just planning an abandoned mine shaft.
Yeah, it looks alright.
What?
Yeah, everyone was making fun of it. And then people actually like it. And does a lot of fan service, I guess, so. I've never played Minecraft, but I know about, like... I know about, like, Technoblade and stuff. What was the thing with the chicken? They're, like, on top of a chicken? Chicken jockey. A rare appearances of baby zombie, zombified pilgrim, baby zombie, baby husk, or baby drowned riding a chicken.
Chicken jockey.
Hmm.
I am the
great mighty poo, and I'm going to throw my shit at you. A huge supply of tish comes from my chocolate starfish.
All right, back into it. I had 3 fails in here, and I don't know why. Ask the bear.
Do you really think you'll survive in here? You don't seem to know which creek you're in.
I notice your issue with the iter method. Let's think about it with the assignment is asking for. The assignment specifies that the iter method should yield each node in the linked list, not just the node's value. When you do node.val, you're only returning the value of the node, not the node object itself. Looking at the linked list to list function in the test file, it's expecting to receive node objects from an iterator because it calls node in links list. Results append to node value. It means that it expects node to be an object with a value attribute. How might you modify your iter method to yield the actual node objects instead of just their values? Just remove the dot val.
Now I'm really getting rather mad. You're like a niggly, tickly, shitty little tag nut. When I've knocked you out with all my bab, I'm going to take your head and ram it up
There we go.
butt.
Your butt.
My butt.
Your butt.
That's right, my butt.
Ugh.
My butt. My butt.
Actually, what are the games that are coming out soon? Game releases April. I haven't heard of any of these. The Last of Us Part 2 Remastered. The Renovator. Today's the 8th. Tiny Garden. Tiny Garden, South of Midnight. Oh, this is not for me. Oh shit, this game comes out today. This one takes place in like the Bayou area of the US. It's kind of interesting. I wouldn't pay for this. Let's see. Let's take a look at this trade that was just proposed to me. Let me ask if you don't mind, how much of a risk is it using an OS without turning secure boot on. Or I don't know. Oh, like a bootloader? When you download a cracked game and you see the command window open up for a second there. You're like, oh shit. Alright, so they're offering Brown. Chase Brown for Kamara and Diggs. See what else they got. I think Brown's gonna be better than Kamara this year. Saints suck. It's only for contact with the computer. It doesn't protect like online, right? In a public setting like the library. Well, I don't know. I don't know much about computer security yet. Soon. No, it's all about security. Like, I wanted to make a directory site. I wanted to make a site that was non-directory, but then like I read into securing personal information from people who come to your site, and like it's a big fucking deal that you secure it properly, especially if they're minors and stuff. So I don't know too much about security, just stuff that I've read on the internet. I actually haven't like learned it yet. How old is Zach Moss? He'd be the handcuff. 27. He's not as good as Brown. too bad. Kamara's been carrying my ass for a long time. Alright, I did it. I don't know why the roster didn't update. I did the trade. I took Brown for Kamara and Diggs. It's the problem is that Diggs is 31 and a half and Kamara is almost 29, whereas Chase Brown's 25, and we play in a dynasty league, so I'm paying for the age. And Brown is durable and he does a lot of touches, so thanks, take it easy. What number is Chase Brown? C2. 30. I don't know any of these games. There's like all the games. I just want like top games to release. Ixion? City Builder. Ooh, that's cool. In outer space. That'd be actually pretty fucking cool. Blueprints. Mystery game. Alice Principle. Puzzle game. Lunar JRPG. Fatal Fury. Oh, is this like Fatal Fury? Fatal Fury? Wow, what a trip. Oh yeah, Expedition 33 looked kind of cool. It's a JRPG. Turn-based, yeah. I don't see turn-based too much anymore. Some remakes are out of town. Wait, Dave the Diver. Why did this come up? Oh, some kind of like expansion's coming for Dave the Diver. Alright, get back into it. So I fucked up. I put yield node.val. It's just yield node because it's node from the main test deals with the node.val. I already got this.
Add to tail. Time to allow our linked list to add new nodes to the end of the list. Kind of like a regular Python lists.append method. Assignment. Complete the add to tail method. It adds a new node to the end of the list and returns nothing. If there isn't a head node, set the new node as the head and be done. Otherwise, keep a reference to the last node in the list. Start with it set to none. Iterate over the linked list. We built this already. Update your last node reference to the current node. Once you've iterated over the entire list, your last reference should be the last node in the list, the tail. Set the next field of the last node to the new node.
Complete the add to tail method. It adds a new node to the end of the list and returns nothing. There isn't a head node. Set the new node as the head and be done. So if not self.head, set it to the new node. Self.head equals new node? Is that what it wants us to do? Otherwise, keep a reference to the last node in the list. Start it with it set to none. Set the new node as the head. But our new node is new node is equal to like node of node. I hate it when it's like that. Node input. Keep the reference to the last node in the list. Start it with the set to none. The last node equals self.head. So that's starting with the head node. And then we gotta traverse, iterate over the linked list. We built this already. Update your last node reference to current node. Once you've iterated over the entire list, your last reference should be in the last node in the list. The tail set the next field to the last node, to the new node. So we need to traverse till we find the last node. So while last node dot next Last node equals last node next. Last node next equals the new node. I don't have the rotations. So it's returning it without quotes. Last node dot last node dot next dot next equals new. If you iterate the entire list, your last reference should be the last node and list the tail. Put the next field to the last node. The last node to the new. Since your method to add tail receives a node object as described in the requirements rather than a node value, why are you creating a new node inside the method with node? Should you directly work with the node passed to the method instead? What happens if you try pre-existing node objects to the method that doesn't work? So it's just new node equals node. So new node equals node. Okay, I was passing it through the function again.
Add to head. For added flexibility, let's allow users to add items to the front of our linked list as well. Assignment. Implement the add to head method. It should add a new node to the front of the list and return nothing. Set the next field of the given node to the current head node. Update the head reference to the given node.
Should add a new node to the front of the list and return nothing. Set the next field, the given node, to the current head node. Update the head reference to the given node. New node. Equals node. New node dot next equals self dot head. Then self dot head equals a new node. Oh, you can just do like set next. Oh. Okay.
Linked list queue. To use our linked list as a fast queue, O1 pushes and pops, we need our add to tail function to be O1. Currently, it iterates over the entire list before appending an item. We can fix this by keeping track of the last item with a new data member, tail. Note, it's common in algorithms to make this kind of trade-off. By using a little extra memory, keeping track of tail, we can make our operations faster. Sometimes you might need to go the other way and use more computation time to save memory. Assignment. Locked-in's queue was working just fine on small datasets, but appending items once the list has 100,000 plus items has started to take a toll on our servers. Implement these changes to speed up our linked list's inserts to O1. Add to head should set the tail reference to the given node if the list is empty. Add to tail should set the head and tail to the given node if the list is empty. Instead of iterating to find the last node, use the tail reference to append the new node. The constructor should set self.tail to none.
Add to head should set the tail reference to the given node if the list is empty. Should be set to the tail reference given node if this list is empty. So just a non one statement. Then reset to the node. Add to tail should set the head and tail to the given node if the list is empty. So instead of iterating to find the last node, use the tail reference to append the new node. To the current tail, new node, self.tail.set next node, and self.tail equals node. The constructor should set self.tail to none. So initialize a tail in the head. Oh. I think it's supposed to be in here. Yeah, same thing, just written in a different order.
Remove from head. We're one method away from having a fully functioning O1 queue. We just need a way to remove the first element from the linked list in constant time. When we're finished, our linked list will fulfill the basic requirements of a queue. add to tail, constant time insert. Remove from head, constant time pop. Let's rename the linked list class to LLQ and remove the add to head functionality because queues don't allow inserting into the wrong end. We've also flipped the arrows in the printed representation to reflect the change. Assignment: complete the remove from head method. It should remove the first node from the list, the head, and return it. If the list is empty, just return none. The head should now point to the next node in the list, if there is one. The tail should be none if the list is now empty. The old head's node should no longer point to anything, tips. If there isn't a head node, return none. Set a temp reference to the current head node. Update the head reference to the next node in the list. If the new head reference is none, set the tail reference to none. Set the next node of the temp reference to none. Return the node stored in the temp reference.
If the list is empty, just return none. The head should now point to the next node in the list if there is one. Split up. Should now point to the next node in the list if there is one. So self.head equals self.head.next. The tail should be none if the list is now empty. If self.head is none, self.tail is none. Welcome to the jungle. Doo-doo. The old head's node should no longer be pointing to point at anything. Self.head.set next. Return self.head. It's only did the first one. Here we go. Just set this set it to a variable. Temp.
Linked list queue quiz. Let's recap a few key points about linked lists and queues. The problem with our array, normal Python list implementation of a queue, was that it had on push operations. The linked list implementation of a queue has O1 push operations. Linked lists are usually a worse choice than standard arrays because they are less performant due to more memory overhead. They are more complex to work with, debug, and reason about. They have no random access, indexing to a specific element. Doubly linked lists are a better choice than arrays in very specific circumstances because they have O1 insertions and deletions at both ends of the list.
Queue made with linked list instead of an array uses less memory. No. It's simpler to implement. No. It's faster to search through. Kinda. Can have 0-1 pushes and pops. It's easier. It's faster to search through. No? Uses more memory. It's more complex. So 0-1 pushes and pops. Huh. Because I knew it kind of wasn't search through because it's more of like, I was thinking of like insertion and deletion, but yeah. A queue that uses an array doesn't have 0-1 pushes and pops because when elements are added and removed from the last index of the array, the items need to shift, which makes 0n time. A normal array. Yeah, that needs to shift, right? The problem with our array implementation of a queue was that it had 0n push operations. So add it to the first index, it takes 0n time. Trees.
Trees are a widely used data structure that simulate a hierarchical, well, tree structure. That said, they're typically drawn upside down. The root node is at the top, and the leaves are at the bottom. Trees are kind of like linked lists in the sense that the root node simply holds references to its child nodes, which in turn hold references to their children. But trees nodes can have multiple children instead of just one. A generic tree structure has the following rules. Each node has a value and may have a list of children. Children can only have a single parent linked list. Node, Nash node, Nash node tree.
Nash node.
Drawn from left to right in this case. Node, 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 node,
No,
node,
node. Multiple nodes in a tree can have the same value. Sure. Yeah. Parent nodes can have blank children, unlimited. And children nodes can have one parent. I just want to see how far we are on this. Oh, we're doing pretty good today. Did more than yesterday. We have 90 done, 70 to go.
Binary trees. Trees aren't particularly useful data structures unless they're ordered in some way. One of the most common types of ordered tree is a binary search tree, or BST. A BST has some additional constraints. Instead of an unbounded list of children, each node has at most 2 children. The left child's value must be less than its parent's value. The right child's value must be greater than its parent's value. No 2 nodes in the BST can have the same value. By ordering the tree like this, we'll be able to add, remove, find, and update nodes much more quickly.
Unbeknownst to our programmer humor, binary trees are actually used in the real world.
Wait, I missed that. if a binary tree wore pants, would he wear them like this or like this?
Unbeknownst to our programmer humor, binary trees are actually used in the real world, not just as fodder in leet code style interviews. Binary trees are the quintessential data structure. They're the ultimate tool for efficiently storing and organizing data. Unlike stacks or queues, a binary tree can be searched for a specific item and can be searched quickly. Binary trees are made up of nodes where each node contains a value and references to at most 2 other nodes, which is what makes it a binary tree. Those 2 nodes are called the left and the right children. The top node is the root, and the tree grows down from the root. So what makes binary trees fast? Well, it's that they are always pre-sorted. Every node to the left of a parent node has values less than the parent, and every node to the right has a greater value. Sometimes a binary tree just stores numbers, which makes...
Oh, so if you look at this, so like this value cannot be greater than 12. It has to be less than 12. That's what I was thinking. I was like, what if this value is higher than 12?
Numbers, which makes greater than and less than operations really simple, but usually they store more complex data like employee information. When they do, we just need to pick an ID, which is just a number, to sort by instead. This less than, greater than structure is what gives binary trees their fast searching capabilities. Let's say you're looking for the number 6 in a tree. You start at the root and move down, and at each node, you decide whether to go left or right by comparing 6 to that node's value. Each time you make a comparison, you're eliminating half of the tree. We don't have to compare against every node in the tree, just one node in each level of the tree. This process is called binary search, and it means that even in the worst case, the number of comparisons is limited to the height of the tree. In big O terms, that means that it takes order log n time to search the tree instead of order n or linear time. If there are 1 million items to search and each comparison takes 1 second, then a linear or order n brute force search takes all...
I get it. So it's like, it looks at 1 million, then 9999, then 9998, whereas the binary is like, it looks at 500,000. Okay, it's less than 500,000. Looks at 250,000. It's less than 250,000.
Almost 12 days. With a binary search tree, it takes about 20 seconds. But it's not just the searching operation that's fast. Inserting, updating, and deleting are all order log n as well. That's why binary trees power databases, file systems, and even Google searches. While you don't get those sexy order 1 operations that you would get with a stack or a queue, at least you can search the thing, something that stacks and queues don't allow.
Interesting. Nodes in a binary tree can have most 2 nodes. Binary search trees, as opposed to generic trees, must be ordered left child, parent, right child.
Insert nodes. The building blocks of a BST are nodes. In our implementation, we will only use a single class, the BST node class. Any BST node is technically also a full binary search tree, with itself as the root node. It's not aware of any potential parents. All our methods that traverse the tree will do so recursively. Have fun. S our locked-in BST node. Throughout this chapter, we'll be building a binary search tree to power Locked-in's custom database. Locked-in's management doesn't trust so-called open source. So here we are. One of the primary features of databases is the ability to look up records by a single key, and binary search trees are the most common way to implement these fast lookups. Each node in our BST will represent a locked-in user. A BST node has 3 properties. Value, the value of the node, a user object in our case, see user.py. You'll notice that users have a name and an ID. Comparison operators are already implemented for you on the class, so you should be able to compare user objects with corpits and 10 directly. The ID is the value that we'll use to determine the order of the nodes in the tree. Left, the left child of the node, another BST node or none. Right, the right child of the node, another BST node or none assignment. Complete the insert method of the BST node class. It takes a value as user class as input and adds it to a new node if the value doesn't already exist in the tree.
Tip, I'd highly recommend using paper and pencil or some kind of drawing tool to visualize the tree as you go through the assignment in this chapter. All right. If the node doesn't have a value yet, just use the given value and be done. So if self dot value is none, self dot value equals value. If the node's value is equal to the given value, just be done. No duplicates allowed. The given value is less than the node's value. And the node doesn't have a left child. Create a new left child node with a given value. If self.left is none. Self.left. EST node. That value. Given value is less than the node's value and the node doesn't exist in left child, create a left with the given value. If the given value is less than the node's value and the node does not have a left child, recursively call insert on the left child with the given value. So else recursively call self.left.insert. So recursively call. Since we already checked if the given value is equal to or less than the node, the value must be greater than the node. Handle whether the node already has a right child. All right, so else if self dot right is none, self dot right equals est load. Else self dot right dot insert value. Recurse your ass.
Insert review. Inserting into a binary search tree, like most of its operations, is very fast. Picture the algorithm that you just wrote in your head. How many comparisons does it take to find the right spot for a new node? It only requires one comparison for each level of the tree, making it O log n, at least in a balanced tree. We'll talk about this later. Order log n is very fast. It's practically as good as O1 in most cases. If our tree has 1,000 nodes, we only need to make 20 comparisons to find the right spot for a new node. If our tree is 2x larger, 2,000 nodes, we only need to make one more comparison per insert, 21 total.
What is the average big O complexity of a dot insert method? Log n. Log in, baby.
Min and max. Some of the simpler BST algorithms are the getMin and getMax methods. Assignment. Now that we can add users to our BST, our systems team wants us to start implementing search functionality. Implement the getMin and getMax methods. They should return the minimum and maximum values in the BST respectively. Tips. The getMin function loops through all the left child nodes and returns the value of the last one. The getMax function does the same for the right children.
So we need to keep going left as long as there are children to the left. And then keep going right as long as there's children to the right. So let's say current node equals self. While there's a current node left, current node equals current node left. Return current node value. And then this is like the same.
Delete. We also need a way to remove users from our BST if a user decides to delete their account. Assignment. Implement the recursive delete method. It takes a value as an input and deletes the node with that value if it exists. Each call returns the new root of the tree or subtree after the deletion. Notice that in the test suite, the delete method is called like this: bstst.delete character. Check if the current node is empty, has no value. If it is, return none. This represents an empty tree or a leaf node where deletion has already occurred. If the value to delete is less than the current node's value, if there's a left child, recursively delete the value from the left subtree and update the left child reference with the result.
All right. Too much, too much, too much. Check if the current node is empty. It has no value. If it is, return none. This represents an empty tree or leaf node with deletion has already occurred. If the value to delete is less than the current node's value, so if the value is less than current code's node value, so self.value. There's a left child. Recursively delete the value from the left subtree and update the left child reference with the result. So there's a left. Self.left equals self.left.delete value. So if value is greater than self.value. Right, we're doing greater than. Delete the value from the right subtree and update the right reference result, return the current node. So it's the same thing, just if self.right, self.right equals self.right.delete value. If the value to delete equals the current node's value, we've found the node to delete. Alright. If there's no right child, return the left child. This bypasses the current node, effectively deleting it. If there is no right child, if not self.right, return self.left. Else if no left child, not self.left, return self.right. Accomplishing the same thing. They're both left and right childs. Children. My childs. If they're both left and right children, we need to find a new successor, the smallest node in the subtree, which is the value next largest after the current node's value. Find the smallest node in the right subtree by walking down the current right child's left branches until reaching the node. Is this where like max and min comes in? So we need the min on the right and the max on the left, right? So successor. Self.right.getMin. And self dot place the current node's value with the successor's value. So self value equals successor. Delete the successor node from the right subtree by recursively calling delete. Self.right is equal to self.right.delete successor. return the current node. Well, one failed. BTS node has no object get min. What were we using on the previous one? Wasn't it get min? Get min. Be right back. Run to the bathroom.
Can't you see? Do you know why we stopped the car?
Do I know why we stopped the car?
Guess.
Guess.
What?
What?
Do you know why we stopped the car?
Do I know why we stopped the car?
Guess.
Guess.
What?
What?
I forgot to close the door.
You forgot to close the door.
Now just don't forget, this ain't kung fu. Come on again. Check and turn the signal to the right.
Check and turn the signal to the right.
Step on the gas, now turn to the right.
We had a failure. BTS node has no attribute get min. What? Just copy this. I just imported the get min function from the previous step that we did, so I could use it. Guys, I think that's gonna be it for me today. I gotta pack some stuff up for eBay's and then run to the post office. So have a good night. Stay safe out there. Don't do too much dumb shit. If you do dumb shit, do one dumb shit thing at a time. And I will be on tomorrow, and we'll just try to finish this up. Binary trees, red-black trees, hash maps, tries, graphs, BFS and DFS, P and NP. Data structures, algorithms in Python. We're gonna finish that up. Or I don't know if we're gonna finish it up, but we'll get a good chunk of it in tomorrow. So peace and chicken grease. I'll catch you later.